Today we're looking at why, according to the lore, Scott Lang should be a human-shaped balloon. Yes, the ones you see in front of Macy's. And if the lore is wrong, then his bones should shatter under his weight, all while owing a 20-ton mass debt to a certain Higgs field. Let's get to the books. We need to talk about inertia. Inertia is basically a particle's stubbornness. It's resistance to any change in its motion. And momentum is just that stubbornness in transit. If the bus were a similar mass to Scott, then Scott would have a chance at moving it. But if Hank is telling the truth about PIM particles and Scott only weighs 190 to 200 pounds, then that's not what would happen at all. This resembles Scott kicking the bus a little bit better. In this case, the bus has all of the inertia, all of the stubbornness, and Scott has no chance of kicking it and flipping it over. So instead of flipping the bus on its side, he's gonna kick straight metal, and he's gonna get flipped backwards. So he's essentially a 60-foot tall inflatable tube man in a gale force wind. Then he has a giant monstrosity kicking a bus on its side. Now, to get the movie's result, Scott needs to be the skillet. And to satisfy the equation, he needs to weigh 20 tons. But mass is far from free, and the collector is waiting. The collector in this case comes from Einstein's famous equation. Energy is equal to mass times the speed of light squared. But hold on, this is just the public perception of that equation. We're missing a little something here. I'm gonna start by squaring the energy term and adding the momentum term. Now, this extra bit isn't necessary for massless particles, like photons. But Scott is very much made of matter, and he has that stubbornness and motion we talked about. So we need the elongated version, the energy-momentum relation. This tells us far more than the original equation. It tells us that massless particles can still have momentum, and secondly, that mass and energy are one and the same. To pull 20,000 kilograms of mass into existence requires 1.8 times 10 to the 21st joules. That is 3 years of the entire planet's energy consumption used in a single second. I put the full calculation in the description, but since we needed energy to get big, we have to give it back when we shrink. Bad news. Shrinking requires us to give off the same energy of 8,000 Tsar bombas. See, that's the kind of bomb that the US is after right now. Scott Lang isn't just a hero, he's a walking extinction level event every time he hits the shrink button. This makes me realize that the government wouldn't care at all about the wasp men from the first movie. They'd care so much more about the annihilation effect of the new bomb that Hank Pym just created. But I digress. Now, if he gets his mass for free and somehow begs the physics gods to let him shrink without devastating amounts of energy loss, then we get to his physical problems. Unfortunately for Scott, he's now a 60-foot tall human being that weighs 20 tons. But his bones are still made of collagen and calcium. The square cube law dictates that while he's 1,000 times heavier, his bone cross-section only grew by 100 times. So his bone strength only increased 100 times, while the mass he has to carry increased 1,000 times. Now that's gonna give us a lot of unintended forces on our bones. And with his mass, his femur is gonna experience 150 megapascals. But Kartik, is that a big amount or a small amount? Well, it's about 21,000 pounds of force per square inch. That's a crap ton of pressure. For contrast, the human femur usually shatters at 170 megapascals. He's at 88% of his breaking point just standing still. That is the pressure found at the bottom of the Mariana Trench. Now, unless Scott has a bone density that rivals a T-Rex, he's gonna destroy his skeleton before he even catches Rhodey. And then there's the Achilles tendon. In Greek mythology, Achilles had one weak point. But for Giant Man, his entire anatomy is that weak point. At 20 tons, his Achilles tendon would snap at the sound of a whip crackling through his calf at subsonic speeds. This isn't just some injury to his Achilles tendon, it's a devastation to his standing. But even if Scott has the bone density of a dinosaur, he needs to eat. I am a regular human and I consume about 3,000 calories a day. But Scott is a 20-ton human. But according to Kelber's law, a 20-ton human needs around 400,000 calories a day just to keep their heart beating. That's 1,500 slices of New York pizza or 700 pounds of steak every single day. Talk about a grocery haul. But here's the problem. If his blood sugar doesn't scale with his size, he'd experience immediate total hypoglycemic shock. He'd become the world's largest fainting goat, which on second hand could be useful to Cap and his team. Scott just falls over and destroys the entire parking lot. Finally, we have to talk about the heat. For us, our main ways of losing heat are actually via our palms, the bottoms of our feet, and our face, which isn't very much surface area, but then again, we're not that large, so it doesn't matter. But when Scott is 60 feet tall and his surface area increases by a lot, then suddenly he's a furnace. He has absolutely no way to cool down effectively. And his temperature would go way past 107 degrees. His neurons would literally start dying because of the heat. Though honestly, with the lower IQ from the brain damage, maybe he wouldn't remember not to get large next time. So maybe it's a self-correcting problem. From the brain damage? So Giant Man wasn't a secret weapon after all. He was a mass-embezzling, bone-shattering, starving radiator that only existed because the laws of physics took a lunch break. A lunch break that Scott's bloodstream desperately needed.